Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL paper from January 2024 for Physics Unit 4. In question number 1, we are asked the number of neutrons in antimony 121. So the number of neutrons would be the mass number minus the atomic number. So this would be 70. So option B is the answer. In question 2, we are asked in which process are electrons released from a heated filament. Since we're told this is a heated filament, this will be thermionic emission. So option D is our answer. Now for question 3, we are given that a proton is traveling at speed v and enters an uniform magnetic field, and the flux density is given 45 millitesla. We are given that force of 135 into 10 to the power minus 13 Newton is exerted on the proton. We have to find which expression gives the velocity in meter per second. We have to use F equals to BQV over here. The force is 1.35 times 10 to the power minus 13. The magnetic field strength is 45 millitesla. So 45 into 10 to the power minus 3. The charge of a proton is 1.6 into 10 to the power minus 19. And the velocity is unknown. If we make V the subject, we'll get 1.35 into 10 to the power minus 13 divided by 45 times 10 to the power minus 3 times 1.6 into 10 to the power minus 19. So option C is the correct answer. Now moving on to question 4. We are given that the structure of nucleons can be investigated by high energy electrons. We have to give the reason behind needing this high energies. The high energies are needed so we can produce short de Broglie wavelengths, because the short wavelengths gives us a greater resolution. C is our answer. Now on to question 5. We are given that a potential difference is applied across two parallel metal plates. So something like this. We are asked how the electric field strength would vary with distance d. In this case, this would be an uniform field because the plates are equidistant from each other. So the electron field and field strength would be constant. So A is our answer. Now in question 6, we are told that a pion can decay into 2 leptons. We have to mark which one of the following 4 is possible. We have to think about the conservation of charge and lepton number over here. Now for the first one, the lepton number on the left is 0. The lepton number of an electron is 1, and the lepton number of an electron neutrino is 1. So we have a lepton number of 0 on the left and 2 on the right. Now for this, the charge doesn't balance out at first. So we have a charge of 0 over here and a charge of minus 1 over here. So this is out as well. This is out. For the third one, the charge again doesn't balance out. We have 0 on the left and plus 1 on the right. So this is out as well. Now for by option D, we have a charge of plus 1 on the left and plus 1 on the right. So the charge balance out. Now if we think about the lepton number, we have a lepton number of 0 on the left. This is a positron. which has a lepton number of +1 and a -1. So the lepton number of an electron is +1, the lepton number of positron is -1, and that of an electron neutrino is +1. So the lepton number on the left is 0 and on the right is -1 + 1, which is 0. So the lepton number also balance out. So D will be our answer. In question number 7, we are given that there is a potential difference V across a capacitor of capacitance C. If that happens, the stored charge in the capacitor is Q. So Q equals to CV. Now we are given that the capacitors are replaced with two capacitors in parallel. So the voltage across both of these capacitors would be the same. So V over here and V over here. This capacitor will have a charge of CV. So this was the previous charge as well. So this capacitor will have a stored charge of Q. This capacitor will also have a stored charge of Q. So the total charge stored would be Q plus Q, which is 2Q. So option D is our answer to question 7. Now in question 8, we are moving away a magnet from the coil, and this creates a current. This induces a current on the coil, which creates a magnetic field around the coil. We have to find which row shows the magnetic pole at X and Y correctly. The magnetic pole at X and Y will be different, so north is out of our options, and so is south. So it can either be B or C. Now if the magnet is moving to the left, the induced magnetic field will try to pull it to the right. So the induced magnetic field will provide a force on the right for the magnet. If it is to do that, there must be a north pole at X and a south pole at Y. So the magnetic pole at X would be north and that in Y would be south. 9, this is we are given that a helium atom of mass m and velocity v collides with a surface at right angle, and the collision time for it to bounce back is given. We are given that it bounces back at the same speed in opposite direction, and we have to find the mean force. We have to use the definition of force as the rate of change of momentum. So force is change in momentum per unit time. So the change in momentum by the collision time. Here the change in the initial velocity was v downwards, the final velocity was v upwards. So the change in momentum, since it was moving downwards at first, we'll take downwards moment to be positive and upwards downwards momentum to be positive and upward momentum to be negative. So the final momentum is minus mv since it's upwards, and the initial momentum is mv. So the final momentum minus initial momentum would be minus mv, so minus 2 mv. So the force would be minus 2 mv divided by del t. So option D is our answer. On to question 10. We are given that a solid line, that this solid line B shows the path. So this line over here shows the path of an alpha particle as it passes close to a gold nucleus over here. We are also given that a second alpha particle with the same kinetic energy approaches the gold nucleus. We have to find out which dotted line shows a possible path. Now we see that the alpha particle is repelled by the gold nucleus, so it moves away. However, in the path A, it's moving towards the gold nucleus, so this is out. Now for path B, so this path over here, It's closer to the gold nucleus, so it should have a greater force on it. It's closer to the gold nucleus than our this path over here, so this should have a greater force exerted on it, and hence it should deflect more than the previous one did. Now for C looks accurate enough. It might be C. Now for question D or option D, it's coming from the bottom of the gold nucleus, so it should be repelled in this direction, so it should have a path like this. So D is also not our option, so C is the correct answer over here. In question 11, we are given a capacitor over here, so this is the capacitor. We are given that the tolerance of this capacitor is plus or minus 20%, and we have to calculate the maximum energy that this capacitor can store. In the diagram, we are given that it has a capacitance of 2200 microfarads and a working voltage of 25 volt. Now, since there is a tolerance of 20%, the maximum capacitance will be 2200 times 10 to the power minus 6 farads times 1.20 to account for the 20% increase that it can tolerate. We get 0.0264 farads. So the energy stored would be half into 0.0264 into 25 square. So work done is equals to half CV square. So we get a work done of 0.825 joules. This is the maximum energy it can store. In question 12, we are given tracks produced by particles in a bubble chamber. We are told that a charged particle interacts with a stationary proton at P, which produces two neutral particles. Both of them are unstable and decays into other particles. We have to explain the evidence provided by the diagram for this description. So after P, we see that there are no tracks leading to here or here or here. So this only happens for neutral particles. So we can say that there are no tracks after P. Which happens due to neutral particles. This describes that two neutral particles are produced. Now we have to explain the evidence which shows that these neutral particles decay into other particles. This proof is present by this. This is the decay, where a positive and a negative particle, two opposite charged particles are produced, same as here. So the V-shaped tracks are subsequent decays. Now moving to question 13, we're given that a helium molecule formed when a proton joined with a helium atom. The helium atom in the helium molecule could lose both of its electrons in a collision. When this happened, the helium ion and the proton accelerated away from each other. The initial separation of the helium ion and the proton was 7.9 into 10 to the power minus 11. We have to calculate the force. The electric force would be kQq by r square. The helium ion had a charge of 2 into 1.6 into 10 to the power minus 19. The value of k is 8.99 into 10 to the power 9. And the charge of an electron is 1.6 into 10 to the power minus 19 divided by the distance between them squared, so 7.9 into 10 to the power minus 11 whole square. The force would come out to be 7.38 into 10 to the power minus 8 newtons. Now we have to find the electric field strength due to the helium ion at the initial position of the proton. The electric field strength is kq by r square. Here the charge we'll use is the charge of a proton, the charge of the helium ion. So k is 8.99 into 10 to the power 9. We'll multiply the charge of a helium ion, so 2 into 1.6 into 10 to the power minus 19. And the value of r square is 7.9 into 10 to the power minus 11. This would come out to be 4.61 times 10 to the power 11 Newton per coulomb. We could also use the formula E equals to F by Q. Here the charge of the proton would be used, so E would be 7.38 times 10 to the power minus 8 divided by 1.6 into 10 to the power minus 19. We'll get the same value from there as well. Now on to question 14. We're told that alpha particles were directed at thin metal foils. This is the apparatus that was used over here. This is the top view of it. We have to describe the observations from these experiments and the conclusions that were made. So this alpha source shoots alpha particles at the thin metal foil. So most of the alpha particles would go straight through, but the ones that come close to the metal foil nucleus, the metal nucleus, they would be deflected. Since the metal nucleus is positively charged, it would be deflected away. So something like this would happen. And some of it would reach the movable detector. We'll move the detector here and there and see where we get a bigger signal. If we see the deflection at a magnified level, these are the alpha particles being shot. It's going towards the nucleus. So if it's going near the nucleus, it would be deflected away from the nucleus and go like this. However, if it's far away, so this will go straight through, this might go straight through or bend just a little. Since the nucleus is very small compared to the size of the atom, most of it will go straight through. So we write that at first. So most alpha particles went straight through. And we have to write what conclusion we draw from this observation. Now we have to talk about these alpha particles which deflected. And if something was directed straight at the nucleus, it would go there and just deflect backwards. So some of the signal would be detected over here and here. At first we'll talk about the ones that were deflected slightly. Now we have to draw the conclusion from these two observations of related to deflection. Since this deflection would show that there was a concentrated amount of charge over here, so the charge of the atom is not spread out throughout the whole atom, it's in a single spot, in a very concentrated spot. So we can talk about that. So this showed that there is a concentration of mass and charge. Now in question 15 we are given the electron diffraction experiment. We are told that a beam of electrons was directed through a thin piece of graphite towards a fluorescent screen. A potential difference of V was applied between the cathode and anode to produce the beam of electrons. From the diffraction pattern, we calculated that the de Broglie wavelength of the electron beam was 2.55 into 10 to the power minus 11 meters. So we use this formula for the de Broglie wavelength. The wavelength equals to Planck's constant by the momentum of the particle. So 2.55 into 10 to the power minus 11 equals to 6.63 into 10 to the power minus 34 divided by the momentum. The momentum of the electron would be 2.60 into 10 to the power minus 23 Newton seconds. Now we know that kinetic energy is p square by 2m, so the momentum square by 2m. We can derive it over here as well, so k is half mv square, momentum is mv. So velocity is momentum by mass. If we put velocity equals to momentum by mass in the formula for ke, we'll get ke equals to half m into momentum by m whole square. So ke would come out to be half into m into p square by m square. So half into p square by m, or p square by twice m. The K would be provided by the potential difference across the between the cathode and anode. So QV equals to P square by 2m. P is 2.60 into 10 to the power minus 23, and we have twice the mass of the electron, so 2 into 9.11 into 10 to the power minus 31. Here the charge is the charge of an electron, so 1.6 into 10 to the power minus 19. If we calculate the voltage, we'll get, so the voltage comes out to be 2320 volts. Moving to question 16, we are given an aeroplane which flies through the Earth's magnetic field. We are given that the airplane is flying with a velocity at 90 degrees to the vertical component of Earth's magnetic field. The distance between the wingtips are given 35 meters. Then we are told that an EMF of 0.4 volts is induced across the wingtips. And from that, the pilot states that the aeroplane is flying with a speed of 250 meters per second. We have to deduce whether the pilot's statement is supported. We are given this information after that. So this is the magnetic field strength. The EMF would be equal to the rate of change of flux linkage, so minus dn phi by dt. Here the value of n is 1 and phi is b times a. So the EMF would be minus the derivative of BA with respect to t. We can write it down as B times dt of A. So the derivative of area per unit time times the magnetic field strength. The EMF would be, the field strength is 41 microtesla. So 41 into 10 to the power minus 6. And the derivative of area with respect to time would be the width of the wingtips multiplied by speed. We can show further working for that. We can break area down into length into width. The width of the wingtips are fixed, so we'll have d dt of L times the width of the wingtips. The derivative of the length with respect to time would be the velocity, and this would be multiplied with the width of the wingtips. So the width is 35 meters and times v We have an EMF of 0.4 volts, so we can place that over here as well. Now we can calculate the value of V. 0.4 by 41 into 10 to the power minus 6 times 35. The value of V comes out to be 279 meter per second. The pilot's estimate was 250 meter per second. This is much greater than that. So the pilot's statement is not supported. Question 17 is about circular motion. So this is the vector. So we have to prove the equation for circular motion with acceleration equals to v square by r using a vector diagram. We can consider this point to be A and this to be B. At A, the particle will have a velocity like this, and at B, the velocity would be something like this. This is VA, this is VB. V and VB would be the same, of the same magnitude. Now if we represent the change in a vector diagram, we'll have velocity of A in this direction, the velocity of B in this direction. The change would be this. This is the change in velocity. This is the velocity at A, this is the velocity at B. This angle over here will be very small, so we can write it a delta theta. Now, since this is a very small angle, we can consider both of them to be right angles. So we'll get tan del theta. You don't even have to use the delta over here. Let me make the working easier for me. So tan theta would be the change in velocity by the velocity. Don't have to write V or VB, both of them have the same magnitude. Now, since theta is very small, we can also write that sine theta equals to is approximately equal to tan theta, and both of them are approximately equal to theta. So we can write that theta equals to the change in velocity by the velocity. Now we also know that the angular velocity is equal to the change in angle per unit time, so theta by t. So we can write theta equals to the angular velocity times the time. So omega t would be equals to the change in velocity by the velocity. Now we also know that the angular velocity is equals to the velocity divided by r. We can use this. So v by r times t will be del v by v. Now we can move the t over here, so we'll get del v by t. Del v by t is the acceleration. So cross multiplying stuff, we'll get v by r times v on this side, del v by t on this side. Del v by t is equals to the acceleration, and on the other side we have v square by r. So we have shown what they wanted us to. Now moving on to part B of the question. We are given a model aeroplane which is attached to a wire and the wire held by a person. Now we are given the details of its motion. So the aeroplane moves in a horizontal circle with radius 28.5 meters, speed of 22.5 meters. We are given that a lift force acts vertically upwards on the aeroplane and that the lift force is equal to twice the weight of the aeroplane. We are given the mass of the aeroplane and a further information that the wire will break if the tension is greater than 35 Newton. We have to deduce whether the wire will break. So we have to find whether the tension will exceed 35 newtons or not for this scenario. So there's a tension over here. We have the weight of the aeroplane over here. The lift force over here, we are given that the lift force would be twice the weight. So 2W. We are also given the radius and speed of circular motion. So we can find the centripetal force or this force over here. If I write this, F would be equal to mv square by r. V square by r is the acceleration and we have the mass over here. So 1.55 into 22.5 squared by 28.5. This is 4185 by 152. Now the weight would be equal to 1.55 g and the lift force would be 3.1 g. Since it's moving in a horizontal motion, the vertical component of t, so this vertical component of t or ty, this would basically be the weight or 1.55 g. We can find that with an equation. So the upward force would be equal to downward force, so 3.1 g would be equal to 1.55 g plus the vertical component of tension. If we calculate this, the vertical component of tension would come out to be 1.55 g. This force over here is the horizontal component of t, so this is Tx. So the tension would be root over Tx squared plus Ty squared. The tension would be 4185 by 152 squared plus 1.55 into 9.81 squared. So we get a value of tension to be 31.5 newtons. This is less than the maximum tension of 35 newton, so the wire will not break. Moving on to question 18. We are given a circuit investigating the charging of a capacitor. The student closed the switch to charge and started a stopwatch. She took a reading every 10 seconds and the graph she got is given over here. we have to determine a value for the capacitance of the capacitor. Well, the equation for charging is V equals to V naught 1 minus e to the power minus t by RC. The value of V naught is 6. You can put it over here. We are given the resistance over here as well, which is 168 kilo ohm. So when the time is equals to the time constant, so T equals to RC, we get the voltage to be 6 times 1 minus e to the power minus 1. So the voltage would be 3.79 volt. So we need to find the value of T when the voltage is 3.79. So we go to the graph, we need 3.79, this is 3.6, 3.7, 3.8. So this is the value of time. The time is this. Each 5 box is 10 units, so each box on the x-axis is 2 units. So this is 32, 34, 36. So the time constant over here is 36. So 36 equals to the resistance into the capacitance. The resistance is 168 into 10 cube. We need to find the capacitance. The capacitance comes out to be 2.14 into 10 to the power minus 4 farads. Now we have to sketch a current against time graph for this. The current would be I naught e to the power minus t by RC. For the current, we'll not have 1 minus e to the power minus t by RC over here. This would be for the voltage. Now the initial current would be V naught by R. So 6 by 168 into 10 cube. This would be 3.57 into 10 to the power minus 5. So a graph like this, and this value over here would be 3.57 into 10 to the power minus 5. We can label the axis as well. This was amperes and this is in seconds. Now in part B, we are told that the student connected a second 168 kilo ohm resistor in parallel with the first resistor. We have to explain how the time taken to charge the capacitor would change. We don't have to do any further calculations, we just have to draw a conclusion. If a second resistor is introduced in the circuit in parallel, the resistance would decrease. So the resistance would halve. So the current in the circuit would increase since V by R is the current. A reduction in the resistance would cause an increase in current. And if the current is larger, the capacitor would charge more quickly. We can also talk about the time constant. Since R decreases, the time constant T will also decrease since the capacitance remains the same and the resistance decreases. This point is more relevant over here. So this is how we structure our answer. So since less time is required to charge the capacitor, the charging would be faster. Now on to question 19. We are given that auroras occur above the Earth's poles when charged particles collide with gases in the upper atmosphere. These collisions produce tiny flashes that fill the sky with light. Now in the question we are told that the collision between electrons and oxygen atoms cause the emission of green light. We have to calculate the velocity of the electrons that would cause the green light of wavelength 560 nanometer to be emitted from an oxygen atom. So this is a question about spectra, but in the first part we don't need to think about the spectra yet. The electron would collide with the electrons in the oxygen atoms, causing them to go to a higher energy level, and when they fall to the ground state, they would emit green light. So we need to find the energy that the electron needs to cause the energy level change. So the energy would be equals to HF. This is the energy of the photon that is emitted. So 560 nanometers is the wavelength. So the energy of the photon emitted would be hc by lambda. The energy would be 6.63 into 10 to the power minus 34 times 560 into 10 to the power minus into 3 into 10 to the power 8 divided by 560 into 10 to the power minus 9. The energy would be 3.55 into 10 to the power minus 19 joules. So half mv square equals to 3.55 into 10 to the power minus 19 joules. The mass is that of an electron, so if its subject V will get 3.55 into 10 to the power minus 19 divided by half into 9.11 into 10 to the power minus 31. So V would come out to be 8.83 into 10 to the power 5 meter per second. Now moving on to part B, we are told that radio waves are also produced during an aurora. Further details. Electrons moving in a circular path in the atmosphere emit radio waves. The frequency of the emitted radio waves is the same as the frequency of rotation of the electron. We're told that an electron with speed 1650 km per second is moving perpendicular to a magnetic field with magnetic flux density 48 microtesla, and that the radio station is broadcasting at a wavelength of 220 meter. We have to find out whether the radiation emitted would interfere with the signal. We are given a hint over here about needing to calculate the radius of the circular path. Since this is moving in a circular motion due to the magnetic field, the centripetal force, so mv square by r, would be equal to the force due to magnetic field, so bqv. The details we do have is the mass of an electron, so it's 9.11 into 10 to the power minus 31. The electron's velocity is 1650 into 10 cube meter per second. squared by the radius. We can remove the square over here since we can cancel the v's out like this. So on the right we'll have the magnetic field strength, which is 48 microtesla, times the charge of an electron, which is 1.6 into 10 to the power minus 19. From this we can calculate the value of the radius. The radius would be 0.196 meters. Now we know that the angular velocity is equals to the velocity divided by r. We also know that the frequency is, or the angular velocity is 2 pi times the frequency. So v equals to 2 pi rf 150 into 10 to the power 3 would be equals to 2 pi times the radius 0.196 times the frequency. The frequency comes out to be 1.34 times 10 to the power 6 hertz. The wavelength, now we have to find this frequency of this station's broadcasts. Since it's a radio wave, the speed is the speed of light, so its wavelength is c by f, the speed of light divided by its frequency is the speed of light divided by its wavelength, which is 220. The frequency is 1.36 times 10 to the power 6 hertz. The frequencies are almost equal to each other, so 1.34 into 10 to the power 6 hertz is almost equal to 1.36 into 10 to the power 6 hertz. So the radiation might affect the broadcast. So this is our answer for this question. Now moving on to question 20. In part A, we have to state what is meant by the principle of conservation of momentum. So this is 2 marks. The first point is gonna be the obvious one, that the total momentum remains constant, or the total momentum before collision is equal to the total momentum after collision. We also have to mention that this has to be in a closed system, or that there must be no external forces on them. So total momentum remains constant in a closed system. Now we are given the diagram of a cloud chamber which shows alpha particle tracks in helium. We are given that an alpha particle collided with a helium nucleus at X, and after the collision the alpha particle moved at an angle of 20 degrees to its initial direction. So at X there was the collision. We have to show that the speed of the helium nucleus immediately after the collision is 5.6 into 10 to the power 6 meter per second. We are given the speed of alpha particle after collision, which is 1.55 into 10 to the power 7 meter per second. So if we break this down, this is the track for the alpha particle, this is the track for the helium. So this is V alpha cos 20 and V helium cos 70 degrees. And if we break down it left to right, on the right we'll have velocity of alpha sine 20 degree, and on this side we'll have velocity of helium sine 70 degree. Since there was no left right momentum at the start, we'll get velocity, the momentum of helium on the left, towards the left. So leftward momentum of helium would be equal to the rightward momentum of alpha particle. So m helium times velocity of helium sine 70 would be the mass of alpha particle times the velocity of alpha particle sine 20 degrees. The mass of helium nucleus is 6.64 into 10 to the power minus 27. The velocity of helium is unknown, so we have to find that, and we have a sine 70 over here. Alpha particles are basically helium nucleus, so the mass would be the same, 6.64 into 10 to the power minus 27 times its velocity, which is 1.55 into 10 to the power 7, and we have to take the left right component, so sine 20. From this, if we calculate the velocity of helium nucleus, we'll get a value of 5.64 into 10 to the power 6 meter per second. So this matches with our answer. Now we have to, we are given that the kinetic energy of the alpha particle was 9.01 into 10 to the power minus 13. We have to deduce whether the collision was elastic. The collision is elastic if Ke before, or total Ke before collision is the total Ke after collision. Now the total kinetic energy before, so initial Ke is given over here, which is 9.01 into 10 to the power minus 13 joules. We have to find the total final Ke. The velocity of, so it would be half into mass of helium nucleus, so 6.64 into 10 to the power minus 27 times the velocity of helium squared, 5.64 into 10 to the power 6 whole squared plus the kinetic energy of the alpha particles, so the same mass over here, and its final velocity is 1.55 into 10 to the power 7. This would be squared as well. So the total final kinetic energy would be 9.04 into 10 to the power minus 13. So almost the same, since 9.04 into 10 to the power minus, this would be 9.03. This is approximately equal to 9.01 into 10 to the power minus 13 joules. So the collision is elastic. Now on to question 21. We have the 6 marker over here. We are told that the idea of an induction cooker was first suggested more than a century ago. An iron kettle was heated by passing an alternating current through a coil wound around a soft iron core as shown. So this is the soft iron core and you have this coils around it. We have to explain why the kettle heats up when there is an alternating current in the coil. Here we have to talk about the change of flux linkage, which would cause an EMF to be induced across the core. So the current would circulate in the kettle. So there would be a circulation of current in the kettle, which would cause a heating effect in the iron kettle. So for questions like this, we talk about the current producing a magnetic field. And since this is an alternating current, the magnetic field would be alternating. So there would be a change in flux linkage. And since alternating current is used, the magnetic field would be alternating. This would cause a change in flux linkage. With the soft iron core. Now this would cause an EMF to be induced in the core. So we talk about the EMF first and then talk about the current. In such cases, the EMF is an important point. EMF is induced, that's why there is a current, not the other way around. And this causes the core to heat up. We need to write about the source of energy for the thermal energy as well. So basically some of the electrical energy would be dissipated as heat. And this thermal energy is transferred to the kettle through conduction, since they're metals in touch. Now moving on to part B. We are told that a manufacturer demonstrated the use of an induction cooker using a raw egg and a steel frying pan that had been cut in half. So this diagram over here, the egg on this half is cooked and on the induction cooker is not cooked. So on the induction area it's not cooked. We are told that the cooker surface is not an electrical conductor. We have to explain why the egg cooks only when it's in contact with the pan. In this case, only the pan would be heated, as there would be no current in the induction area since it is not an electrical conductor. So even if an EMF was induced, the induction area would not cause a flow of current due to the induced EMF. However, in the steel pan, if an EMF is induced, a current would circulate, causing a heating effect. So the surface of the cooker does not get hot. You could also state that only the pan would get heated since it is a conductor while the surface is not. Now in question 22, this is about subatomic particles. We're told that kaons are short-lived subatomic particles, also known as K-mesons, and these were the first strange particles to be discovered, so meaning that it contained a strange quark. we have to explain the structure of a K minus meson. Masons are made out of it's made out of one quark and an anti-quark. So it will be made out of one anti-up and one strange. The charge of anti-up is -2/3 and that of strange is -1/3. So this will have a charge of -1, which matches our question. We have to explain the structure as well. So the meson must be a quark anti-quark pair with charge -1 and must contain a strange quark. Now we are given that the mass of a K minus meson is 494 mega electron volt per c square. We have to calculate the mass in kg. So 1 MeV per c square basically means, if we go from the base as well, we know that energy is mc square. So the change in energy can be written as the change in mass times c squared. So if we make del m the subject from here, we'll get del m equals to change in energy per c squared. Now if we write the change in energy in mega electron volt, the unit of mass comes out to be mega electron volt per c squared. This is how it is. This is how MeV per c square is a unit of mass. Now at first we have to change this 494 mega electron volt into joules. So we have to multiply it with 1.6 into 10 to the power minus 19. This is mega, so we'll have a 10 to the power 6 over here. So 7.904 into 10 to the power minus 11 joules. So the mass would be 7.904 into 10 to the power minus 11 divided by c square, so 3 into 10 to the power 8 whole square. The mass comes out to be 8.78 into 10 to the power minus 28 kilograms. Now in part B, we are asked a question about cyclotrons. In this question, we have to explain how a cyclotron produces a beam of high energy particles. We have to refer to the alternating potential difference and the magnetic field over here. So here the electric field would accelerate the particles, while the magnetic field keeps the particles in circular motion. and we have to talk about the alternating part of it. So every half cycle the polarity of the D's change, so we have to talk about that as the last point. So this is our answer to part B1. Now moving to part B2, we are given that the first cyclotron made by Lawrence in 1929 produced a beam of protons with a maximum kinetic energy of 80 kiloelectron volt. We have to calculate the magnetic flux density of the magnetic field used in this cyclotron, given that its diameter was 0.11. At first we'll convert the energy to joules, so 80 into 1.6 into 10 to the power minus 19. Since there was a kilo, we'll have a 10 cube over here. So this is 1.28 into 10 to the power minus 14 joules. Now we know that K E equals to P square by twice M. So the momentum would be root over twice M times the kinetic energy. So the momentum of this proton would be root over twice into the mass of a proton, which is 1.67 into 10 to the power minus 27. This would be given over here. So mass of a proton times its kinetic energy, so 1.28 into 10 to the power minus 14. So if we calculate the momentum, it comes out to be 6.54 into 10 to the power minus 21 Newton seconds. Now since the particle is in circular motion, mv square by r would be equals to bqv. The v cancel out. mv is equals to the momentum, so the momentum divided by r equals to bq. So the momentum is bqr. So 6.54 into 10 to the power minus 21 would be the magnetic flux density times the charge of protons, so 1.6 into 10 to the power minus 19, and the radius would be 0.11 by 2, so 0.055. From this, if we calculate the magnetic field strength or magnetic flux density B, it would come out to be 0.743 Teslas. And that's it for this paper.